Hello, Professor. My name is TONGWEN, and today I will be sharing my research on analyze the impact of urban air quality on public health in the United States using machine learning models. This study was done under the guidance of Dr. Karakiwa at the School of Management. Now let's turn to abstract problem statement. Urban areas are growing fast, and with that, air pollution is becoming a bigger problem. The World Health Organization says air pollution is a major health risk, but figure out how different environmental factors affect our health is tricky. That's where machine learning comes in. We use advanced techniques to analyze lots of data and under these complex relationships better. We had four main goals for this study. First, to see how urban air quality affect public health. Second, to test different machine learning models to find out which one predict health risks best. Third, to identify the key environmental factors that influence these health risks. And lastly, to provide useful insights for policymakers and city planners to help reduce these health risks. In public health, machine learning helps us handle huge and complex data. We checked out six models: linear regression, random forest, XGBoost, SVM, KNN, and natural networks. Each has its good and bad points for studying how air quality affects health. For example, linear regression is simple but cannot handle complex panel. Random forest and XGBoost manage tricky data well, but are harder to explain. Knowing this is help us pick the right model and improve feature research. We used a dataset called Urban Air Quality and Health Impact Dataset from Kango. It has 1,000 records and 46 features. The key the key data points include weather details like temperature and humidity, air quality measures such as PM2.5 levels, and health risk scores. This data covers multiple cities across the United States, giving us a broad view of different environment and these health impacts. First we clean the data by removing any duplicate entries and get rid of unnecessary features that didn't help our study. Then we filled in missing values, used the median for those columns. Next, we picked the most important features by looking at how these correlate with health risks, and using a random forest model to see which ones matter the most. We also removed any outlier to make our data more reliable. Finally, we split the data into two parts: 80% for training our models and 20% for testing them. We test six different machine learning models. The first, linear regression. Second, the random forest. Then XGBoost. The four, support vector machines. 5. K-nearest neighbor. 6. Artificial neural networks. We measured each model's performance using three metrics: mean, squared error, R squared, and explained the variance score. This helped us see which models work best. Let's talk about which factors are most important. Our analysis showed that dew point is the top predictor of health risks, followed by severity score and wind gust. Heat index and maximum temperature also play a big role. This factor help us understand how different weather conditions impact health risks related to air quality. When we compared the models, the random forest came out on top with an R-squared of 0.9705 and the lowest mean square error of 0.0118. XGBoost was close behind with an R-square of 0.9608, and the key nearest neighbor also performed well with an R-square of 0.9682. This enable method did a great job capturing the complex relationship in our data, outperforming simpler models like linear regression. Here are our main findings: extreme temperature can increase health risks by 50 to 20%. Higher humidity make pollution effects worse. Wind panel affect how populace spared. These are differences in health impact across different regions and seasons. These insights show how various environmental factors work together to influence public health. Our study has a few limitations. The data is only at a city level, so we might miss variation within a city. We also didn't include socio-economic factors like income or housing quality, which can affect health. The data is daily, so we might miss short-term population peaks. Additionally, some of our models, like natural networks, are hard to interpret, make it tough to explain exactly how they make prediction. Finally, we didn't use real-time monitoring data, which could make our finding more applicable in real-world situations. To wrap up, machine learning models, especially ensemble methods like random forest and XGBoost, are very effective at predicting health risks from urban air quality. We identified key environmental factors that influence these risks, providing valuable insight for policymakers. For future research, we suggest integrating real-time air quality data, including socio-economic factors, using more detailed time data, developing models that are easier to interpret, and focus on neighbor-level analysis to get even better results. Thank you for your listening. I'm happy to answer any question you might have. Thank you, Professor.